So in this work, flavors from fractals, what we are trying to do is we're taking two different concepts of flavors from particle physics and the concept of fractals, which is a nonlinear concept from classical phenomena. So we're trying to get some insights about the flavor physics in particle physics from the fractals. So to give a brief introduction about flavors, now in standard model, it is known that the different types of fermions which are there, they are found in three copies. So one of these is lighter, one is heavy, and third one is even heavier. Now this trend is observed for both leptons and quarks, and they have same quantum charges under gauge groups, but they differ from each other in their masses. So their mass scales are different. Now further, the mixings of these fermions, it's also not uniform. It varies. So for the neutrinos, the mixing is much more. For the CKM or the quarks, the mixing is moderate, and for the charged leptons, there is a small mixing. So in some sense, from these simple you can say the gauge charges, we are getting some complex Yukawa we can say Yukawa parameters which are accounting for the masses and mixes by some phenomena. Now people have tried to account for different masses, how you can produce the different mass scales to move away from the Higgs wave scale. So the famous neutrino mass some mechanism works on that you consider some high energy or more massive field and couple it by the standard model field, and then you will get sufficient small enough scale. Now people have tried various other mechanisms such as radiative correction model, and then there are linear chain masses model, or there are extra dimension model where they localize the wave function on different sites to produce different mass scales. Now more than that, there are also models to explain why there are only 3 copies, when there can be more than 3 copies, 2 copies, 4 copies or something. So people have also tried to come up with some models which are these string extra dimension models, where they consider some kind of T branes and then they intersect each other and produce these 3 numbers. Similarly, there are mechanisms to explain the intergenerational mixings too. So the overall motivation is that there is something physics, some underlying physics, fundamental physics, which is going on at some higher energy scale or small length scale, which when we look at in the standard model, what we are getting is the effective physics. So such as an example is shown in this slide. It shows the linear chain mass model. So there are these extra high energy physics fields which are coupled to each other in a certain way, and when you integrate out these heavier modes, what you get at the small scale is a coupling y effective, which is not really the fundamental parameter. It is the effective parameter that you get once you integrate out these fields. So the motivation is that there is some underlying fundamental mechanism going on, which at lower energy scale gives us the standard model. Now, so moving along that motivation, we wanted to use fractals because of some of the properties of fractals which are unique to them, such as they are self-similar. That is, if you take a fractal and then you zoom on the fractal, then after a while you get the same structure. So in a sense that even if you change the scale, you get the same properties for the fractals. So this can be vaguely related with the fact that we have these 3 copies which have the same properties, but they were at different mass scales. Now furthermore, the fractals have non-integer dimensions or fractional dimensions, which is very unique to them, and even though being very complex, they can be generated naturally with the simple transformations. So you start with some simple structure, and then you consider again a simple transformation on that structure, and then you apply the process iteratively. So as the iteration goes on, you get more and more complex structure. So more often fractals are produced by recursive process, so they can exist in nature, and they have been found in nature in various places such as coastlines, snowflakes, on the cloud formations, and the tree branches, etc. So people have because of this iterative process and this non-integer dimension, people have used this fractal in further theoretical sciences, in computer science, biology, and recently in quantum computing too. Now it's not that fractals have not been used in the context of high energy physics. So there is a paper by Professor Hill. His paper is came around 2002, where he tried to use the fractals to produce extra dimensions which are fractional. They don't have integer space-time dimension, but they are fractional. So here what we are doing is a bit different. We are not trying to account for extra dimension. What we are doing is we are trying to use these complex structures since they have good connectivity. So they might account for intergenerational mixing. So that was one of the motivation more, that maybe they can also account for generational mixing apart from that different mass scales. So the idea that we are implementing in this project is we are taking the case as an example case and the Sierpinski triangle. So this is the triangle that is found after 2 iterations, the second one. So it has 15 nodes. So the number of node of the current graph you can find by 3 times the number of node of the previous graph minus 3. So you start with 3, 3 times 3 minus 3, next is 6, 6 times 3 minus 3, this will be 50. So that way we thought of working with this structure. It looks sufficiently complex and it has good connectivity. So this is our example case. Now what do you mean by node? We are implementing this in the context of deconstruction formalism. So we will apply it in the theory space. So when you have 2 nodes connected, so at each node in the context of fermions, we have left and right fermions. So when 2 nodes are connected, let's say node I and node J, that means the fermions of Li and Rj are connected, and also Ri and Lj, they are connected to each other by some coupling strength. So we can get this picture, and the corresponding Lagrangian, we can write it as this. Now there are some formalism such as this clockwork formalism, which also works on these theory space models, but it's a linear chain model. It does not have this 2D fractal structure, it's just a linear chain. So but the clockwork has this left-right asymmetry. So it has n number of left-handed fields and n plus 1 number of right-handed fields. Here we are putting them on same ground. So we have 15 left and 15 right here. Now since clockwork has this asymmetry in left and right, so what happens is when you write the mass matrix, you get the rectangular mass matrix. So from linear algebra, there is a result that says that if you have a rectangular mass matrix of n by m dimension and your m is greater than n, then you will have at least m minus n 0 modes. So clockwork models, they guarantee at least 1 0 mode because they have n and n plus 1. So the difference is 1. Now once you have a 0 mode, the other thing is to produce the smaller mass scales, you need to localize the 0 mode. Once you have 0 mode localized, then you can couple the Higgs with the standard model and get the sufficient whatever mass scales you require. So clockwork has that freedom that doesn't matter what kind of matrix you take, whatever element you take, it will have the 0 mode. The only constraint you need to take into account is the fact that that 0 mode has to be localized. So in this paper that mentioned here, we have looked at some of the explorations, what we can do, changes we can do, but still retaining the localization property. Now with this structure, this fractal structure that we have considered here, we don't have that privilege. Since we have 15 left and right fields, there is no asymmetry in them, so mass matrix will be square matrix. So in general, there's no need to be any 0 mode. But with this structure, there were 3 0 modes. Now the fact that there was 3 0 modes, we can relate it with the fact that in the standard model, we have 3 copies, that is 3 generations. So in a sense, it is naturally explaining why we have 3 flavors in the standard model. Now the other thing is that those 0 modes, once they are produced, they need to be localized. Now if you consider any graph randomly, the modes, they might not be localized. More often, they will not be localized. And same was the case here, it was not localized, just as in clockwork. So what we do is, for that, when 2 nodes are connected, node I and node J, then there is this coupling parameters Q's which are connecting 2 nodes. Now what we can do is, another linear algebra result we can use, which says that when you have a matrix A which has some n number of 0 modes, then from that you can construct a matrix B with same number of 0 modes, but if you consider the element wise transformation which is separable, then your 0 modes, they will be localized. So using that theorem, we can pick out these Qij's in this way. This is just one of the example. One can take other functions to localize it. So with this, what we are getting is, we are getting one graph which is producing 3 0 modes which are localized. Now unlike clockwork, so clockwork one chain produces one generation. So to produce 3 generation masses, you take 3 different chains and they are independent to each other. You can take whatever different number of nodes or different Q parameter, but we don't have that freedom here. We cannot introduce one more node here, 16th node or something, because this is found by that fractal pattern, fractal transformation. Plus we have only one parameter f here, we don't have 3 parameters there. So we cannot localize our 0 mode as what we want. So there is these models are very constrained. We cannot just get any numbers out of this that we want. But still, when we look at the 0 modes and the localization of the 0 modes in these patterns, we see that, for example, we have given this one left and one right 0 mode. So there are 3 of these. Now they will be localized. So because of the factor of Q that we have chosen. Now the other fact is that these 0 modes, there are 3 0 modes, so they are localized at each node by different extent. So one is localized at, let's say, 15th site, one is localized at 14th site, and if you're looking at their contribution on 7th site, so they will have different amount of overlap or the component on that site. So naturally, what you're getting is different extent of localization of zero mode just by one structure. So you don't need to consider different independent structures and then consider one structure to explain one mass and their mixing. You can just take one structure, it will say you have 3 modes which are localized, and then you can produce 3 different mass scales naturally. The below 3D diagram, it shows the localization of zero mode. So in the context of, if you consider that Sierpinski triangle, so that's how they're localized. And as you can see, on somewhere the 8th node, they have some component, some overlap is there. Now once you have these properties of these zero modes and they are produced and they are localized, then what you can do is you can again couple your Higgs on some of these sites. Now we have chosen these sites, and it turns out that when we choose these sites, these 3 zero modes which are produced, they have different extent of localizations, so they are producing 3 different mass scales naturally. So to come to the numerics, the results that we got. Now in principle, this fractal can produce 3 different mass scales. It can also account for 3 intergenerational mixing, because at each node their zero modes have some components, so zero modes can mix among themselves too. So in principle, this can also account for intergenerational mixing and their different mass scales, and also why there are 3 flavors. So if you look at the numerics, so this is done, the order calculation is done. So we were trying to see if for the lepton sector, charge lepton order mass ordering can be produced. So we were able to produce the GeV, 0.5 GeV and 1 MeV mass scale, which is of the order of lepton, muon, and tau. And we know that they don't have any mixing, so we can find the parameters where there was no mixing, but these mass scales are also produced. And this plot that we have shown here, this is a plot which shows that how these 3 different mass modes or zero modes that are produced, their scale varies how with the parameters y, z and f. So what we think is that if we increase the value of f, our localization of the zero mode will increase. So if there is more localization, we can think that the mass scale is going down, and that is what we expect, and that is what we get. As we move from left to the right, you're seeing those mass scales. This is log of mass scale on the y-axis, so it goes down. Now if it is written 20,000, it's not the value of f. The value of f there is 2,000. You have to divide it by this, or sorry, 2. You have to divide it by factor of 10,000. And if you look at 40,000, the value of f is 4. So you see, by the value of f equal to 9 or 10, you are getting a mass which is 10 to the minus 12 order suppressed from the fundamental scale mass. So with the natural orderings and natural parameters at the fundamental scale, you can account for the hierarchy masses too. Now the problem is that if you localize your zero modes too much, so since they are localized too much, they don't have very much mixing among them, then their mixing will go down. But to produce neutrino masses, we know that they have to be very much suppressed, because if you start from TeV or even Higgs level scale, you need 10 to the 12 order or something like that, GeV order compression. So that requires a big localization, but that requires a large mixing from experimental side. So this can be done. We can not go as far as 10. We can restrict ourselves to around 4 or 3. There the mixing is large. We can get the PMNS mixing, and at the same time, to lower the scale, we can use those Y couplings. Now we have tried to account for these quark sectors too. So in the quark sectors too, we were able to find the parameters f and y, which were able to produce the quark masses and their mixings, the CKM mixings, except for the top mass. So to give the summary, standard model has this 3 generations of particles. So particles, they come in 3 copies, and they have different mass scales, and they have intergenerational mixings. Now people suspect that there might be some more fundamental physics which is going on in there, so they come up with some other mechanisms. So we tried to use fractals for this fact, because fractals have connectivity, and so we were capable to produce these intergenerational mixings, and it is mass with the help of just one graph. We didn't need 3 generations. So as an example case, we took Sierpinski fractal, and it was able to produce the leptons and quark masses and mixings. So with that, I've left. Thank you for attention.
Thank you for the institution.